Good morning everyone. My name is Pranav and I am from Institute of Aeronautical Engineering IRE studying in CSC AIML section C, and today the subject is essential problem solving, and today we are gonna discuss the topic efficient algorithms for solving the traveling salesman problem, which is one of the most interesting topic in essential problem solving and some difficult. Introduction to traveling salesman problem, also known as TSP. The traveling salesman problem TSP is one of the most famous problems in combinatorial optimization. The main objective is to find the shortest possible route that visits each city exactly once and returns to starting point. We also have the real world examples like delivery and logistics routing, microchip manufacturing, DNA sequencing, network design. Know for being NP hard, meaning it cannot be solved efficiently for large inputs using traditional methods. So basically, the traveling salesman problem is like uh, its main purpose is to find the shortest possible route that visits every city exactly once, only once, and returns to the starting point again. Coming to the formal definition, given a complete weighted graph G equal to V, where V is set of vertices, also known as nodes, and E is edges representing path between cities, and C of I comma j is cost or distance between cities I and j. Find a Hamilton cycle of minimal cost. Minimize sigma I comma j belongs to 2c of I comma j and text minimize, or sum I comma j in text tour c of I comma j minimize I comma j belongs to 2 sigma c of I comma j, subject to visiting each vertex exactly once. So formal definition is like consider a graph G of VE, where V is like set of vertices which are also known as nodes, and E is like edges representing path between cities. And the classification of TSP is symmetric TSP, STSP. So that actually there are two types of classification: symmetric TSP, STSP, and asymmetric TSP, ATSP. So first coming to symmetric TSP, also known as STSP, is C of I comma j is equal to C of j comma I, which means distance between cities is same in both the directions. It's like traveling to from school to home in a straight path, no any deviations. You will get the distance between the two places same. And asymmetric TSP, ATSP, is like C of ij is not equal to C of gi. If any equation is added to C of ij, then it is equal to C of gi. It is common in real world transport networks with one-way paths or different traffic conditions. Computational complexity. TSP belongs to NP hard class of problems. Time complexity for exact algorithms grows exponentially of n factorial. For large graphs, n is greater than 20. Brute force or excessive search becomes computationally infeasible. Hence, efficient algorithms and approximations are essential. Coming to the applications of engineering, computer science, routing in data networks, mechanical engineering, tool path optimization in CNC machines, in electrical engineering, VLSI circuit design and component placement, in civil engineering, transportation and delivery route optimization, in AI and robotics, path planning for drones and autonomous vehicles. So basically, there are so many applications used in different branches, as you can see in computer science routing in data networks, in mechanical engineering, tools path of optimization in CNC machines, in electrical engineering, VLSI circuit design and component placement in civil engineering, transportation and delivery route optimization. And in AI and robotics, it's like path planning for drones and autonomous vehicles. Coming to the Navy approach, which is brute force, it is enumerate all possible tours n factorial, calculate total distance for each, choose the minimum cost tour. The advantage is always gives optimal solution, and the disadvantage is exponential time, impractical for large graphs. So it is like it takes lot of time and it can't manage the large graphs. And coming to branch and bounce method, searches the solution space intelligently, uses lower bounds and pruning to skip impossible branches, works by exploring only promising routes. The main advantage of it is finds exact solution for moderate sized problems, and the disadvantage is it is still exponential in worst case. So branch and bound method is also typical for it is hard to use for large graphs. And coming to heuristics algorithms, heuristics provide good but not necessarily optimal solutions quickly. Common heuristics methods: nearest neighbor NN, greedy algorithm, insertion heuristics, cheapest, farthest, nearest insertion, two optimal or three optimal methods, and Christophite's algorithm, route scheduling for robotic systems, airplane route planning, DNA sequencing order optimization. Coming to nearest neighbor algorithm, which is also known as NN. Start from a city. At each step, visit the nearest unvisited city. Return to the start when all are visited. The time complexity will be like O n2 into O power n2. The process is simple and fast. It may give poor results for complex graphs. Greedy algorithm. Choose the shortest edge that doesn't form a cycle or increase degree greater than 2. Continue until all vertices are connected. Approximation ratio usually within 25% of optimal for random graphs. Often used as an initialization step for advanced algorithms. And coming to second optimization and third optimization, it is used to improve an existing tool. Coming to second optimization, it removes two edges and reconnect to reduce total distance. Third optimization is like same idea but replaces the two optimization. In two optimization we use two edges, but in three optimization we replace it by three edges. Interactively refines until no improvement is possible. Efficient for large instances when combined with heuristics. Coming to Christophite's algorithm, provides a guaranteed upper bound on tool length less than or equal to 1.5 optimal. The steps are: first one, find minimum spanning tree MST, and second one, find vertices of odd degree and perform minimum perfect matching. Third one, combine to form Eulerian circuit, shortcut to TSP tool. And fourth, the final one is the complexity O n cube into O n power 3. Best deterministic approximation for metric TSP. Meteoristic approaches used for large scale TSP, hundreds or thousands of cities. They balance exploration and exploitation to find near optimal results. The main methods are genetic algorithms, also known as GA, simulated annealing, also known as SA, and colony optimization, also known as ACO, particle swarm optimization, also known as PSO, and taboo search. So first genetic algorithm. It is inspired by biological evolution. Each tool is like a chromosome. The operations use make like selection, choose best tools, crossover, combine parts of two parents, mutation, randomly alter tools, iteratively improves fitness for shorter distance, excellent for large graphs when exact solution is impossible. Coming to anti-colony optimization, ACO, paths with better results, more pheromone, more likely to be chosen, gradually converges toward near optimal tool. The main strength is handles dynamic and large TSP instances effectively. Coming to simulated annealing, SA randomly perturbs solution, accepts worse moves occasionally to escape local minima. Slowly cools down system, stabilizes at good solution. And coming to the conclusion, TSP remains a benchmark problem in optimization and computer science. Exact algorithms useful for small or medium instances. Heuristics, methodistics essential for large scale practical problems. So basically TSP is also used in real time applications as we have seen in computer science engineering, it is used in electrical engineering, it is used in mechanical engineering, in robotics also. So the main conclusion is it remains like a benchmark problem in optimization, and exact logarithm useful for small or medium instances, but for large instances it is still a mistake. And for heuristics and methodistics essential for large scale practical problems. Thank you.